Most people think Ohm's law is just a formula that must be memorized. But in engineering, this is not correct. In this video, we will understand Ohm's law clearly from the fundamental level and see why it is one of the most important relationships in all of electrical engineering. Ohm's law describes the relationship between voltage, current, and resistance in an electrical circuit. It is one of the most fundamental laws in electronics and electrical engineering because it connects the three quantities we have already studied. The law states that the current flowing through a conductor is directly proportional to the applied voltage and inversely proportional to the resistance of the conductor. The mathematical expression is V equals IR. In this equation, V represents voltage measured in volts, I represents current measured in amperes, and R represents resistance measured in ohms. Ohm's law is not simply a mathematical shortcut. It describes a physical relationship observed in many electrical materials and circuits. If the voltage increases while resistance remains constant, more current flows. If resistance increases while voltage remains constant, less current flows. Understanding this relationship allows engineers to predict circuit behavior before building a design. To understand why Ohm's law works, consider what happens inside a conductor when voltage is applied. First, a voltage source creates an electric field within the conductor. This field provides energy that encourages free electrons to move. Second, as electrons move through the material, they encounter resistance caused by collisions with atoms and imperfections in the lattice structure. The electric field tries to increase electron motion, while resistance opposes that motion. The balance between these two effects determines the amount of current that flows. When voltage increases, the electric field becomes stronger, causing more charge to move through the conductor each second. When resistance increases, collisions become more significant, reducing charge flow. Ohm's law mathematically describes this balance between driving force and opposition. Rather than viewing it as a formula to memorize, engineers see Ohm's law as a model that explains how electrical systems naturally respond to changes in voltage and resistance. A useful analogy is water flowing through a pipe. Imagine a water tank connected to a pipe. The water pressure inside the tank is similar to voltage because it provides the driving force for movement. The flow rate of water through the pipe is similar to electrical current because it measures how much material moves through the system over time. The size and roughness of the pipe represent resistance. A narrow pipe restricts flow, while a wider pipe allows more water to pass. If you increase the water pressure while keeping the pipe unchanged, the flow rate increases. If you keep the pressure constant but make the pipe narrower, the flow rate decreases. This behavior is exactly what Ohm's law describes in electrical circuits. Although electrons and water are very different physically, the analogy helps build intuition for understanding the relationship between voltage, current, and resistance. Ohm's law is used constantly in engineering practice. It is often the first equation engineers use when analyzing a circuit. Suppose an engineer knows the supply voltage and resistor value in a circuit. Using Ohm's law, the expected current can be calculated immediately. This helps determine whether components will operate safely. Engineers also use Ohm's law when selecting resistor values, designing voltage dividers, estimating power consumption, and troubleshooting faulty circuits. For example, if a measured current differs significantly from the expected value, it may indicate a damaged component, wiring problem, or design error. Even highly advanced electronic systems containing microprocessors, communication modules, and RF circuits still rely on the principles described by Ohm's law. Although modern systems can be extremely complex, the relationship between voltage, current, and resistance remains one of the foundational tools used to understand circuit behavior. In RF engineering, Ohm's law remains important, but its application becomes more sophisticated. At low frequencies and DC conditions, resistance is often sufficient to describe how a circuit opposes current flow. However, at RF frequencies, inductors and capacitors introduce additional effects that depend on frequency. As a result, engineers expand the concept of resistance into a more general quantity called impedance. Impedance still follows an Ohm's law relationship, but it includes both magnitude and phase information. This allows engineers to analyze signals that vary rapidly with time. Transmission lines, antennas, filters, and amplifiers all rely on impedance relationships derived from the same fundamental principles introduced by Ohm's law. For RF engineers, understanding Ohm's law is therefore the first step toward understanding impedance matching, power transfer, standing waves, and signal integrity. The equation may appear simple, but it forms the foundation of much more advanced RF design concepts. So today, we learned that Ohm's law describes the relationship between voltage, current, and resistance, rather than being just a formula to memorize. We went from definition, mechanism, intuition, engineering, view, RF application, to build a complete understanding of the concept. This foundation prepares us for the next topic, electrical power, where we will learn how circuits transfer and consume energy. Thanks for watching. See you in the next video.